We're continuing 7.4, integration of rational functions by partial fraction decomposition. And now we're going to tackle case 3, in which we have an irreducible quadratic factor in the denominator for this rational function that we want to integrate. So, our decomposition supposes that if we have some q of x with a factor of the form ax squared plus bx plus c, which cannot be reduced. So to be clear, it's not factorable, which is irreducible. Then the partial fraction decomposition has a term of the form ax plus b, these are the capital letters that are undetermined coefficients, over ax squared plus bx plus c. And you'll notice now this is slightly more complicated than what we started with. So rather than each factor getting its own letter, now each one gets 2, actually. So the best way to look at this is to just kind of dive in. So our first example, we'll just start with we'll start with an example in which we have one irreducible quadratic factor and we still have some maybe repeated linear factors. So we're going to evaluate the integral of x squared minus 29x plus 5 all over x minus 4 squared times x squared plus 3 dx. So you notice that x minus 4 squared is a repeated linear term. So we're going to have 2 terms there, one with x minus 4 and one with x minus 4 squared. So repeated twice. And our irreducible quadratic form here is x squared plus a 3. We know that this is irreducible because it gives us, this is only, so I'm getting too much into the theory here, but let me actually talk about it. So when we're talking about polynomials with real number coefficients, they're irreducible if and only if when you set them equal to 0, the only way you can't factor it any further to get an equivalent statement that has a real number coefficient. So the only way we could factor this in some more complicated system would be if we wrote x minus I root 3 times x plus I root 3 equals 0. In which case we could see that this is linear, but this involves complex numbers. So really we can't do this. All right. So, and besides, we don't even use complex numbers in this class, so we couldn't. Right. So this means that our desired partial fraction decomposition will take this original rational function and write it in this form. A over x minus 4 plus b over x minus 4 squared plus cx plus d over x squared plus 3. Okay. Then we know that we're going to end up with 4 unknowns to solve for, 4 equations. We really should be using Gaussian elimination to solve this. And again, I'm going to do some long-winded, horrible thing that you're going to want to skip through, but, it's helpful to see it. Okay, so let's go ahead and solve this. We're going to put it in the equivalent linear system form. So multiply by the least common denominator, which is the original denominator. So x squared minus 29x plus 5 equals a times x minus 4 times x squared plus 3 plus b times x squared plus 3 plus cx plus d times x minus 4 squared. Okay, good so far? Great. So what can we do here now? Well, let's go ahead and multiply this out. So we have a times x cubed minus 4x squared plus 3x minus 12 plus b times x squared plus 3. I'm going to leave that alone for now. Plus, and I'm going to do this multiplication in 2 steps as well. Cx plus d times x squared minus 8x plus 16. Okay. And then we get ax cubed minus 4ax squared plus 3ax minus 12a plus bx squared plus 3b plus cx cubed plus dx squared minus 8cx squared minus 8 d, sorry, let's see, x plus 16 cx plus 16 d. Okay, just double check that, make sure that that checks out. Okay, now remember that we're looking at equating coefficients, so there's no x cubed term on the left side, which means any x cubed term, any x cubed terms are going to go equal to 0. So that would be this plus this. Any x squared terms go with 1x squared, and that's going to be, let me use a different, squiggles means x squared terms. Squiggle, squiggle. Okay. And then curved line like that means x terms. Curved, curved. And then the ones that are not highlighted are going to go with the constant terms. Okay, so all told, that means we have, you may or may not be hearing my daughter squealing in delight. I don't know how much you can hear actually in these videos, so if you hear any background noise, I'm sorry. Okay, so x cubed terms, remember, those are the just straight across underline. Ax cubed plus cx cubed, which means 0 equals a plus c. Okay, so a plus c equals 0. All right. Now, x squared terms, remember they're going to equal to 1. We have negative 4a plus b minus 8c. So, to clarify, negative 4a plus b minus 8c plus d equals 1. Okay, look so far? Look good so far? Okay. Next, the x terms. We have 3a no x terms with b, it appears. Yeah, no x terms with b. So 3a plus 16c minus 8d equals negative 29. Okay, that I'm pretty sure you can hear. Okay. And lastly, constant terms, we have negative 12a plus 3b plus 16d. Plus 16d, yeah. Does that look right? Yeah. Equals 5. Okay. So you can solve this in any way that you want. Just be aware that if you're going to solve this using Gaussian elimination, it's going to be very, very long, okay? Because the equivalent augmented matrix form is going to look like 1, 0, 1, 0, 0, negative 4, 1, negative 8, 1, 1, 3, 0, 16, negative 8, negative 29, negative 12, 3, 0, 16, 5. Okay. So that's the augmented matrix that gives us the equation that we want. Okay. So when we do this, then that means we're going to be trying to get it in the form that looks like this. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and then some the values here, C1, C2, C3, C4. That hopefully are going to be the answer, right? And if you carefully go through this, okay, I think I am just going to end up skipping the work here because it's just going to be way, way, way too long. Or no, maybe we should do it. Does it build character? I think it builds character. Okay, well, you can skip it if you want, and you can go straight to the numbers or do it some other way that you want. But starting from the base step, okay, let's try to strategize. So what do we need to do? So if our technique here is going to require us to have a leading 1 in the first row, that means we're going to have to multiply the first row by 4, negative 3, and 12 in order to get rid of the first 3 numbers in the second, third, and fourth rows, okay? So we can do that in 3 steps, okay? So first of all, let's go ahead and highlight that we're going to take row 2, we're going to replace it with row 2 plus 4 times row 1. What that ends up looking like is, so 4 times 1 is 4, plus negative 4 is 0. 4 times 0 is 0, plus 1 is 1. 4 times 1 is 4, plus negative 8 is negative 4. 4 times 0 is 0, plus 1 is 1, augmented with 4 times 0 is 0, plus 1 is 1. Okay. And you know what? Why don't we go ahead and do the same thing with row 3. We're going to replace row 3 with negative 3 times R1, okay? And that's going to give us, so remember, this is this is this, all right? So negative 3 times 1 is negative 3, plus 3 is 0. Negative 3 times 0 is, okay, so we get zeros again. Negative 3 times 1 is negative 3, plus 16 is 13. The 0 again doesn't change what we have there. And then negative 3 times 0 is 0, yeah, again. That doesn't change, all right. I don't want to do any more than that in one step. So our next line here, 1, 0, 1, 0. So the top row doesn't change, but the middle two rows do change. So we're going to replace those with the rows that we just replaced them with. So not too bad. Making good progress here. Notice that we don't have to do anything too drastic with rows 2 and 3 now. They're almost set up in a way where we can, easily keep working toward the objective here to get that middle diagonal of just ones. And here again, so row 4, we're going to replace with row 4 plus 12 times row 1, because that's what's going to give us that cancellation. And that is going to look like, I'm going to write that over here. So 12 times 1 is 12, plus negative 12 is 0. Again, if we have a 0, that doesn't change the value in that row. Great. 1 times 12 is 12, plus 0 is 12. Another 0, so that doesn't change the row's value. 16, augmented with, and then a 0 again, so that's going to be 5. Okay, so in our next step here, we have 1, 0, 1, 0, 0, 1, negative 4, 1, 0, 0, 13, negative 8, and 0, 3, 12, 16. Now we augment with the corresponding, sorry, that should be a 1, negative 29, and a 5. Okay. All right. Next, I want to get rid of the 3 in the last row. So I'm going to work with row 4 again. So row 4, I'm going to replace with row 4 plus negative 3 times row 2 now. I'm going to work with row 2 because I don't want to add anything to the first column in row 4, but I do want to use that 1 already to simplify it. So that gives us the new row. So we're going to keep that 0 in the first spot. The second spot is going to be negative 3 times 1 is negative 3, plus 3 is 0. Negative 3 times negative 12, sorry, negative 3 times negative 4 is 12, plus 12 is 24. 1 times negative 3 is negative 3, plus 16 is 13. And 1 times negative 3 is negative 3, of course. Plus 5 is 2, positive 2. So we now have 1, 0, 1, 0, 0, 0, 1, negative 4, 1, 1, 0, 0, 13, negative 8, negative 29. And then our last row becomes 0, 0, 24, 13, 2. Okay, so the numbers are getting a little complicated. That's not a problem. What can we do now? Okay. Then what we can do is I'm going to go ahead and divide the fourth row by 24. Yeah. Or actually, I'm going to use the 4, yeah. No, let's try to get rid of this 24. So we're going to multiply row we're going to replace row 4 with row 4 plus, and if you want to, the surefire way to get rid of that 24 is going to be, you're going to need to multiply by the right number. So first of all, make it opposite sign of the number that is there already, so negative. And then if you want the original number to become negative 24, then you need to multiply it by 24 over whatever number that is. So negative 24 over 13, row 3, which looks not fun, but we're going to have to carefully do this one then. So that row then becomes, I'm going to do this, in more than one step because it's a lot of work. So that last row, right? So 0 plus, so any row that has zeros, you're not going to change. You're not going to change much. So 0, 0. Now 24, we're adding negative 24 over 13 times 13. So that's the third spot. And then the second spot is going to be 13 plus negative 24 over 13 times negative 8. Augmented with, so I ran out of space here, but I'm going to try to do it in the bottom line. 2 plus negative 24 over 13 times negative 29. Oh boy. Okay. So we're quickly running into some problems here. So that first spot though so the first spot that's non-zero is going to turn into a 0 because if you see, you get cancellation of the 13, so you just get 24 minus 24. So that's going to be fine. So we end up with 0, 0, 0. The next spot, on the other hand, you're going to get two negatives make a positive, so 8 times 24 over 13 plus 13. This is going to be 13 plus 8 times 24, or 24 times 8, or 13. And if we, if we want to get this to be, the same fraction, then we should go ahead and actually adjust that. The last one, so the augmented part, again, we're going to have a fraction that's probably going to have a 13 in the bottom, so 2 times 13 over 13. Two negatives that cancel out, so we get 24 times 29 over 13. Wow, that's not nice. All right, so then this is the point probably where you would need a calculator. So 13 times 13 is 169 plus 24 times 8 is 192 over 13. Similarly, 2 times 13 is 26 plus 24 times 29 is 696 all over 13. So remember, we're still trying to figure out what that new row is going to have to be. So 169 plus 192 is 361 over 13. And 26 plus 696 is 722 over 13. Now he had better hope that reduces into something nice. So 361 divided by 13 is not an even number. In fact, they share probably nothing in common, but you should check some divisibility things like, can you divide it by 3, or by 7, or by 8, or by 9, or by 11. Actually, there's not much here that I think you can do. Except it turns out that 361 is 19 squared, so whatever. As for 722, divide that by 13. That also gives you nothing. Okay, that's fine. We will not get into that. But that's our new row. So that means our system now becomes... Yeah, I know. No, this part is not fun. But you just got to follow your nose and hope that things settle into place. So 1, 0, 1, 0. 1, 0, 1, negative 4, 1. 0, 0, 13, negative 8. And the last row, of course, we just found 0, 0, 0. 361 over 13. All over. No, sorry, not all over. Augmented with. And the last row is going to be 0, 1, negative 29. And 722 over 13. Now, one nice thing here that's going to happen, notice that if we multiply both sides, so I'm gonna adjust row 4 one more time. So row 4, I'm going to replace with, I'm going to divide by 13 over, sorry, 361 over 13, which means the same thing as multiply by 13 over 361, which should give us, again, 0, 0, 0. That first spot, that last spot is going to go to 1. And now, hopefully, this is the point where we're going to get some nice cancellation. So 13 over 361 times 722 over 13. The 13s cancel nicely. But 722, is that divisible by 361? Aha! We've done it. This is actually going to be 0, 0, 0, 1, 2. So it does end up being something nice because 722 divided by 361 is 2. That means our system becomes 1, 0, 1, 0, 0, 1, negative 4, 1, 0, 0, 13, negative 8, 0, 0, 0, 1, 0, 1, negative 29, 2. Okay. Now, at this point, it's not actually that bad because now we can work our way backwards and we can do some nice cancellation of the numbers that we have up here. So, for instance, at some point, we should get rid of this negative 8, which we can do by multiplying row 3, or sorry, adding a copy of row 4 to row 3. To cancel that negative 8, we should multiply row 4 by 8 and then add that to row 3. So what will that give us? That should give us 0, 0, 13, because the row 4 and the first 3 spots is just 0. Then 8 times 1 is 8, times negative 8 is 0. And then 8 times 2 is 16, plus negative 29 gives us negative 13. That's nice. 1, 0, 0, 0, 0, 1, 0, 0, 1, negative 4, 13, 0, 0, 1, 0, 1, and 0, 1, negative 13, 2. Okay, now you can see that row 3 is actually going to end up working out nicely as well, because we're going to replace row 3 by dividing both sides by 13. So 1 over 13 times row 3. And you can see pretty clearly, I'm not going to write out the intermediate work. You're going to see pretty nicely there that you're just going to end up with a 1 in the 13 spot and a negative 1 in the negative 13 spot. So you can see that, once you work through the hairy details, this actually becomes kind of fun. Okay? And now we can cancel some of the remaining non-leading coefficients. So for instance, we want to target this 1, this negative 4, and this 1. Okay? And we can do that in a couple of swift steps. So first of all, row 2, we'll replace that with row 2 plus negative row 4. That'll get rid of the 1 in the last spot there. And we can replace row 1 with row 1 plus negative row 3, because that's going to get rid of the other one in the row 1. Okay, and I'm not going to do the intermediate work. We're just going to plug that right in. We know that that's going to take care of this one and this one. So 1, 0, 0, 0. Negative 1 times negative 1 is positive 1. Plus 0 is 1. 0, 1, negative 4. And then negative 1 times 1 is negative 1, plus 1 is 0. Negative 1 times 2 is negative 2, plus 1 is negative 1. If it's still confusing to do it in more than one step, don't skip the steps, it's fine. Because our very last step here then is going to be replacing row 2 with row 2 plus 4 times row 3. And notice that all that will do is it's going to change the negative 4 into a 0. And then negative 1 times 4 is negative 4. Plus negative 1 is negative 5. So finally, all said and done, our system becomes the equivalent linear system 1, 0, 0, 0. The top augmented number is 1. 0, 1, 0, 0. And then remember that's going to turn into a negative 5 because negative 1 times 1 times 4 is negative 4 plus negative 1 is negative 5. 0, 0, 1, 0, negative 1. And 0, 0, 0, 1, 2. Okay, not bad. Equivalently, this is the same as the system A equals 1, B equals negative 5, C equals negative 1, and D equals 2. We did it. Okay. So this is the point now where I'm like, okay, so what did we actually start with? Remember that what we started with was the integral of x squared minus 29x plus 5 over x minus 4 squared x squared plus 3 dx. What we were converting that into was a over x minus 4 plus b over x minus 4 squared plus cx plus d over x squared plus 3 dx. Okay. So this will reduce, and we can pull out the a and the b. That's no problem. A is just 1, so that's not a problem. So integral of 1 over x minus 4 dx. I'll just write that as dx over x minus 4. B is negative 5, so minus 5 integral of dx over x minus 4 squared. And then plus the integral. This one's different. This could be negative x plus 2 over x squared plus 3 dx. So I'm going to set this piece apart, okay, because the rest of it we already know how to handle. It's this piece that we need to handle, okay? So I'm going to do this in a separate step. So what is this integral? This is standard for when we're working with irreducible quadratic factors, that we're going to need to split this into 2. So we're going to split it into a rational with an x in the numerator and the one with just the number in the numerator. So this is allowed, right? We're totally allowed to do this. Here's why we need to do this. This one we can handle with a substitution. So we're going to let u equal x squared plus 3, which means du equals 2x dx. And if we want to replace the x dx, then we'll just recognize that we're going to end up multiplying by negative 1/2. This one, on the other hand, we need to use a the arc tangent or the inverse tangent rule. Okay, so tan inverse rule, and we'll get into that in just a second. First, let's handle this first integral, which is if we do the replacement with the du, we're going to end up with so 1/2 du equals x dx. So we're going to have negative integral 1/2 du over u, okay, then plus this part, right? So we're gonna get into that in a second, don't worry. This first one, remember, is just gonna be negative 1/2 ln of absolute value of u. So that part's pretty much handled. We're just gonna replace u back. It's this one now. So if we pull out the 2, we have dx over x squared plus 3. Because we're using the rule, the integral of dx over x squared plus a squared equals 1 over a tangent inverse of x over a plus c. But we're not going to add the plus c yet because we're doing that later. Okay. A squared, though, here is 3, which means our a is actually the square root of 3. So this means this becomes negative 1/2 ln of absolute value of x squared plus 3 plus 2 times 1 over the square root of 3 tan inverse of x over square root of 3. And then the plus c part, right? So plus c, and I'm going to call that plus c1, okay? All right, all of this work that we did was just for this segment, right? Remember that we still actually had to solve the rest of it. So back to your regularly scheduled programming. The first one is a simple natural logarithm. So the integral is ln absolute value of x minus 4 plus, or minus 5, but there's going to be another negative, plus 5 times 1 over x minus 4. Because remember, that's the one with, if you have a square in the bottom, you're actually using the power rule. Technically, you'll also have to use the substitution rule, but when you substitute u with x minus 4, it doesn't change the fact that dx is just replaced literally with du. The last part then is the part that we just found, this piece. So negative 1/2 ln of x squared plus 3 plus 2 over root 3 tan inverse of x over root 3 plus c1 plus c2. So technically there was another integration, constant of integration. Again, it doesn't matter. We're going to replace it with some other constant of integration. So lastly, all of this is ln of absolute value of x minus 4 minus 1/2 ln x squared plus 3. Really here you don't actually need parentheses because it's always going to, you don't need absolute value bars. It's always going to be positive, so it doesn't matter. Plus 5 over x minus 4 plus 2 root 3 tan inverse of x over root 3 plus c, some other c that we don't know. And that's it. That's the answer, right? So, wow, yeah, it's a lot. So I'm going to split this actually into 2 videos. So that's part 1. We did one full example where we used the Gaussian elimination that ended up using a huge chunk of our time. And then in the next video, we're going to do another example where we have to do the long division first. And then we'll do one more example that just illustrates a more general strategy that we actually kind of talked about here in this intermediate work where we split up the the rational function that has the linear on top and the quadratic on the bottom into actually two kinds of integrals. One that we end up using a u sub on, and another one that we end up using the tan inverse rule on.